All right, so we want to factor this sucker, but first, before we jump in with both a physical model and kind of a representation of that physical model, I want to do something a little simpler so that we can get a grasp for how this works. So let's start here with x squared plus 5x plus 6, and we'll use our algebra tiles to factor that. So let's just draw this. There's an x squared. How do we know this is an x squared? Because this length on the side is x. Get my pen out. This is x. And this is x, and x times x is the area of this rectangle, or in this case square. So this is a square of area x squared. And then I need 5 x's, and the same kind of logic applies. We're just going to kind of line them up. We know that the length of this side is x and the length of this side is x. And if this long side has a length of x, then the short side has a length of 1. So this is 1x, but we need 5 of those. 3, 4, 5. Then we need 6 little ones, like this. And now our job is to make this into a nice little rectangle. And we know that because in factored form, we're going to see something that is one thing times another thing. So right now, this distance is x plus 5. And this distance is 1. And that doesn't include all the information we need. So we're going to kind of play around with that until we get it to be a nice little rectangle and the area is as expected. So I'm just going to start dropping tiles in here. You can rotate these sideways, and if we do it this way, we can only get 4 of those ones in, so that's not quite far enough. So let's see what happens if we take another one of these and kind of move it down here. And it turns out that does fit nicely. And now we factored this. And it really is that easy. This is x plus 2. And this one is x plus 3. So our factored form x plus 2 times x plus 3 with our physical representation of what that looks like. So one thing to point out here is that this kind of C times A method, where you're saying I need 1 times 6. So I need something that multiplies to 6 and something that adds to 5. Well, that would be 2 and 3, right? And this tells us right off the bat what these numbers are going to have to be. So you can see already that there's a relationship here between this box method, that some people will call that, and the physical representation. But you actually don't need to know this information to mess around with your tiles and get the representation like that. All right, so the question is then, what do we do when things don't match up nicely? And what if we have negative numbers? So I want to walk through that real quick. We're going to do a very similar example. Let's do 2x squared plus x minus 3. And I've already checked that this actually does factor. So we have two things going on. We have some negative values, and we also have a number that isn't 1 in front of our x squared term. So to solve this out, first let's, to factor this rather, let's start putting our pieces out. We have 2x squareds, 1x, and negative 3. Now, one fact about algebra tiles, if you're using them, it becomes very difficult to combine negatives and positives on the same in the same place. So if you are using negatives and positives, like for example this, it's important to make sure that your negatives are in one place and your positives are on the other side. That makes your life easier. It's not impossible to do it the other way, but it's harder to track. So in any case, here we have represented kind of everything that's going on. And I think you can see that, I mean, we don't know how long this x is in terms of ones, so there isn't really a nice way to figure out what's going on. So we're going to have to start adding 0 pairs. So a 0 pair would be an x and a negative x, for example. You can see that zeros out if we put them together, to kind of see if that will help us with what we need. So we're going to put this x here and this negative x down here. And we can see that we still need another negative x. So if I need another negative x, I need another positive x. There's my other 0 pair. We'll throw that in there. And then magically, there are 3 spots left. All right, so what is this in factored form? Well, we can see that there's 1x minus 1. And then we have our 2x's. So that's x plus x. And then plus 3. Right? And then if we go back to our kind of algorithm method where we're saying our 2 times our -3 results in -6. So we need a number that multiplies to -6 and then adds to 1, the coefficient of that x right there. What are those numbers that multiply to -6 and add to 1? So things that I always like to start with things that might multiply to 6 and add to 1. So 2 and 3 can get me to 6 and can get me to 1, but I got to figure out where the negatives are going to go here. And like that. Okay. And now if you look, that -2 and that +3 do not show up in an obvious way in our model. And so that doesn't become obvious how these things right here are related to our model until you factor by grouping. So let's go ahead and do that. Start here, and we're going to take our x term and we're going to split it up into -2x and +3x, which is exactly what we did in our model. There's -2x and +3x. So let's just kind of follow that. -2x and +3x. And then we still have our -3. And then here our model has already told us what this factors to, but algebraically we still have one more step. And that is we're going to factor each group right here with its greatest common multiple on the outside. So here we can pull out a 2x, and we're left with x minus 1, excuse me. And then in the second pair right here, we can pull out a 3, which leaves us with an x minus 1. And if you do this right, if this part went successfully, then you'll always see this will always match. So the thing that you factored will be the same. And as you notice, I can actually pull an x minus 1 out of here, which leaves me with 2x plus 3, and then the x minus 1 that I factored out as well. And that's the same conclusion that we drew up here, our 2x plus 3 and our x minus 1. So I think that this model kind of shows us how the physical tiles relate to what's happening with the grouping and with our zero pairs. So now let's do the problem that you asked to do right at the start. All right, so I do recommend before watching the video that you give this a try yourself using the tiles to see if that method makes sense. I think that the tiles are probably the most accessible for students. And then that really shows you how the grouping method also links into how those tiles are working. So now we need 11 x's. I'm going to pause the video. Groovy, just double checking here. We have 3 x's. We have 3x squared, excuse me. We have 11 x's, and we have -4 tiles. So with the physical tiles, generally red will represent negative, whereas blue represents positive. I think that's how that works with most of the ones I've seen in person, but you can define that however you want. So, okay, we'll do the same sort of process. I'm going to start pairing up these x's, maybe like this, I don't know, and see where they go. And if you're a student, you really can figure it out just by playing with it, but it's not necessarily obvious how that's going to turn out. Right, so I'm just going to play with it and see what a student might do, and then where they're going to get stuck, and how the Xbox thing that we did might be helpful. So when I've lined them up like this, we notice that we have 4 1s, or 4 negative 1s, but this is a positive 1. So I'm going to need somewhere a -1 to be part of my side length, which means I'm going to need a negative x in here. And if I add a negative x, I got to add a positive x. So we have our 0 pair, 0, right? All right, so this isn't going to work. I'm going to have to put these back up to the top. Give me a second. And that's a lot of x's for just one row. And I'm actually suspicious that maybe I should have put them down here where they would stack a little bit better, times 3 instead of times 1. But I'm going to try this and see what happens. So if I have 1 here, I'm going to need some more. So let's pull out some more. If I add another one, there's my 0 pair. If I add another one, there's my 0 pair. And it's okay to add 0, right? That doesn't change anything. So we put those up there. This happens a little faster in person than on the computer. And if this were the case, I would have however many x's that is of -1s. That's far too many. So I'm actually going to switch places with these x's and these negative x's. All right, cool. So now I can see I've kind of moved my swap sides with the positives and negatives, and I can see that I really needed one more here so that I could have one more on the bottom as well. So I'm going to add that 0 pair and then put it in. And this leaves me in a really nice place because we have 4 of these and kind of 4 slots here. 1, 2, 3. But something's going wrong here. And as you can see, this length is not a -1. That's a positive one. Right? So what's going wrong here? Why isn't this working? I want you to think about that for just a moment. So we're noticing that we need a whole bunch of rows here of these -1s, and that these -1s don't line up nicely with the positive ones on this side, right? So maybe we could actually cancel out some of our 0 pairs here. Maybe we didn't need as many as we thought we needed. Let's see what happens. There we go. Hey, that's interesting. Oh, I'm liking where that's going. Okay, cool. So that factors nicely, and our final factor is x plus 4, and then we have 3 x's in this direction minus 1. Now you can cheat a little bit, and you can skip all this playing around using the method that we already talked about with our a times c on the bottom, so -12, and then our b on the top. So we need 2 numbers in these slots that multiply to -12 and add to 11. And I think the 2 numbers that do that are 12 and 1, with 1 being negative. And now this right here tells us exactly how to break up our tiles and what 0 pairs we need. How do we know? Well, I need 12 x's, which are right here. I started with 11. I actually needed 12, so I'm going to need 1 more x. And then I need 1 negative x, which is right here. And so if you start here, you can still use the tiles and kind of cheat a little bit so that you don't have to do it by grouping. I'll still show that so that you can see how those are related. And then we'll be done. So for example here, we noticed that we needed 12 x's and -1 x's is the way we would break up our 11x in order to factor this. So we have our 3x squared plus 12x minus 1x minus 4. And we can factor our first group and then factor our second group. The first group's greatest common multiple is 3x, which leaves us with x plus 4. And the second group's greatest common multiple is actually just -1, which leaves us with x plus 4, as it should. If it doesn't, then you didn't factor it the right way in your first step up here. Right, and we can see that up top as well, that when we pull out the x plus 4, we have a 3x minus 1 and an x plus 4, which matches what we have, 3x minus 1 and x plus 4. Hope that helps.